Good evening. After the answer to that last question, I'm not quite sure how to introduce Pam as anything other than someone who just amazes me. I'm John Grant. I'm a senior geologist in the Museum Center for Earth and Planetary Studies, and I'd like to welcome you to the third in this year's Exploring Space lecture series. I want to make sure to mention that this program is made possible by the very generous support of our sponsors, Aerojet Rocketdyne and United Launch Alliance. These are both, I was going to say to thank them in a moment, but let's do it now. These are both companies that have been instrumental in launching and propelling many spacecraft that have explored the solar system over the years. And then I'll move on to Pam, who I'm very happy to introduce tonight. She, as you know from having talked with her for a while, is an astrobiologist and mineralogist at NASA's Goddard Space Flight Center. She's also the deputy principal investigator for the Sample Analysis at Mars Instrument, or SAM. That's how I work with her most often. That's currently on the Mars rover Curiosity. Her research involves pretty much everything, as we've heard, but I'll say here that it involves the habitability of planetary surfaces, and she's done extensive field work in both Arctic and Antarctic environments, deserts, and the seafloor. Please help me welcome Pam Conrad.
Thank you. Okay, so now comes the time where you will be able to ask the questions you want to ask. The thing about life is you can't separate it from where it lives. You can't separate its origins from the conditions of the place where it came to be. So when we think about whether life is extreme or not, it's kind of a funny concept. Because if we imagine the Earth at the time life may have evolved, or at least we know it had evolved a long, long time ago, those conditions were really different than they are now. And we would consider them extreme. The life that we got originally looked a lot different from the life that we have now, but some of that life still has descendants that we can recognize. So what I hope we'll do tonight is talk a little bit about the environments, a little bit about the life, talk about how, as I said earlier, they're entangled, and then try to get a handle on how these things help us explore other planets and how what we learn on Earth about life might help us to predict what we should look for about life and potentially habitable environments on other planets. So I think the best place to start is with my favorite planet, this one. And it's probably my favorite planet because I live here. And the reason why I live here is because over time, not only have we evolved here, but we, by being here, have optimized this planet for us. When we talk about the possibility that we might harm the planet, we are probably not going to destroy the planet per se. As a ball in space, it will persist, even if we blow ourselves up with nuclear weapons. But what happens as we are thoughtless about the environment or our use of resources is that it becomes less optimal for us. So that is something that we can dismiss as a fear that we'll destroy the Earth. We should never dismiss the possibility that we'll destroy the environment that we need to be alive in. And that is something that is already happening. We are past the point of no return for trying to understand whether we can limit the effects of humans on the environment. But we can alter the trajectory going forward. I'd like you to know that this image is an actual image taken by remote sensing, and that little swirl of stuff just off of the mid-Atlantic coast is Hurricane Irene. When we look at the Earth, we can see a lot of things about it right away. Someone asked earlier about what we learn from remote sensing and its utility in understanding astrobiology. From remote sensing, you could look at the Earth and know that it was inhabited. And in fact, that experiment has been done. It was done a long time ago by Carl Sagan using the Galileo spacecraft to turn around and take a look back at us. It was predicted before that even by scientist James Lovelock, originator of the Gaia hypothesis, that we might be able to determine whether or not a planet was habitable by looking at its atmosphere and trying to understand whether or not the normal rules of chemistry that we can observe apply, or whether there were some anomalous things happening that you couldn't explain by any other process than something like life. In the case of Earth, we have a disproportionate amount of gases that shouldn't coexist together stably. And that's one hint that we continue to do something on Earth that's creating that weird mix of gases in the atmosphere. If we take a look at a little bit smaller spatial scale, a little bit closer range, we see some things here that immediately indicate life. We look at this and we say, this is not an especially extreme environment. We see the clouds, which indicate that we probably get rain there. We see what looks like a meandering, healthy river, and we see green stuff on the sides, which designates plants. So we can look at this and we can say, life is here. But when we take a look at other bodies and we see images like this, it's a lot more cryptic. We have no rule of thumb to go by, and we have to ask ourselves, what is it that we can say for sure about life on Earth, which is universally applicable to these other places? That's a really hard question to ask, because the only life we've ever found so far is the life that's here. So making a statement about universal applicability is really challenging, because how do we know? So what we try to do is take a look at the environment and understand what is it that that environment supplies that life might be able to use. If you take this approach and try to understand what the environment provides and think about some of the kinds of things that life does, then you can begin to draw an association between the environment and the organism. If you start with organisms that you know really well, yourselves, or some of the other kinds of organisms that live together with you, for example, the microbial content of your gut, some of the vegetables that we eat, other types of agricultural products, such as livestock, you begin to see clusters of associations. Now you're looking at a broader base of organisms. It's a community. And you have to understand whether or not you have raw materials that support that whole community. If you think about where that stuff is distributed on the Earth, you begin to see patterns. Patterns for requirements of, say, temperature, requirements for oxygen, for pressure, for amounts of water, for the type of water, for trace chemical elements, for certain types of textures of soil, so on and so forth. We have planetary scale requirements, and I'll talk about those again in a moment, for things like, say, protection from ionizing radiation such as galactic cosmic rays or solar energetic particles. These planet scale things are also useful because when we look at those as they relate to Earth and we ask ourselves if other bodies have such protections, then it gives us a sense of whether or not an organism on a body that doesn't have such a protection would need to evolve some mechanism for protecting itself, or whether it would inhabit some other part of that planet. So, for example, if you look at Mars, and by the way, none of these are to scale. Mars here is the biggest because that's the one that I'm getting paid to study. No, just kidding. I am getting paid to study Mars, but the reason it's biggest is just because I wanted to spend a little more time talking about it. In the case of Mars, something really bad happened to Mars a long time ago. It lost its internal dynamo, and it then lost its protective magnetic field. So all the galactic cosmic rays that are streaming out come to the surface of Mars. There's a lot of ionizing radiation. There's a lot of solar energetic particles. the atmosphere is very tenuous, thin, and so you get a lot of UV of a much more energetic wavelength than on Earth. So on Mars, you would require some kind of protection. One way you might get that if you were an organism is to live underground, a lot underground, say maybe 15 meters underground. So those are the kinds of things that you try to think about when you try to understand the likelihood of life somewhere and how extreme in life's ability to adapt it would have to be in order to thrive. Some of these other bodies here, so you see the moon in the upper left. We don't think that life is possible on the moon. We don't think that the moon is as promising an environment for a number of reasons. One is that the moon is pretty much an airless body. It is true that the moon is critical in the habitability of the Earth. So in a sense, the moon plays a very important role in enabling life here, whether it's extreme or let's just say nominal life. I'm going to debate what extreme is in just a moment. The orb to the upper right is a picture of Europa, the Galilean moon. It's gotten a lot of attention because it looks like it has a subglacial ocean, and you see lots of these linear features on the surface where it looks like you get some cracking of the ice, movement of the ice, probably tidal bulging because of the humongous planet that's next to it. And so the question is, does stuff come up from the ocean that is beneath the ice and give us clues as to whether or not there's life there? So that's an interesting question. I think that if you look down to slightly to the right and all the way to the lower right-hand corner, that's Enceladus. And I think you've probably all heard stories about plumes of geysers and potential water there as well. So I've mentioned water a few times. We always talk about water. We talk about water as essential to life. We always talk about water as a solvent. I love water for a completely different reason, and that is because water has amazing thermal properties. Water is fabulous. It absorbs infrared, and water, because it absorbs infrared, by the way, is a blue molecule. It reflects back blue. So that's a good piece of cocktail party trivia. Water is essential not just as a solvent, but also because of its thermal management. I think you've probably heard stories in other kinds of lectures and in textbooks about how miraculous it is that ice is less dense than the liquid form of water, and that if that were not so, life in liquid bodies would die as it gets cold because the ice would form and sink and freeze from the bottom all the way up to the top. So the fact that water is denser than water ice is fabulous for life. Now, I spend a lot of my time, as I told you, exploring Mars with Curiosity rover. And when I look out in an environment like this, it looks to me to be very different than the environment that I showed you a couple of slides ago. The beautiful river, the puffy clouds, the gorgeous green. And yet, I've been to the Mojave Desert a number of times, and I can tell you there are places in the Mojave Desert that don't look that great either. However, you don't see any area of the Mojave Desert that is completely naked. So when I look at Mars and I see this picture, I am absolutely compelled to ask, can anything live here? And as I ask myself, can anything live here? And I try to understand not only what the requirements would be for life there, I can do a parallel process here on Earth, and this is where we introduce extremophiles. Because what we can do on Earth is ask ourselves, if one particular trait that is required on Earth, if you just modify it a tiny bit, could you go a little more extreme? Maybe a little bit colder, a little bit drier, a little bit more radiation. How far can you go? What can you do? How much more clement does an environment have to be to become habitable? Is there a gradual change? Is it a sharp boundary? So that when I look at an environment like this, I don't just look at this environment as completely barren. I look at this environment in terms of environments on Earth that are challenging, where there's a lot of life, and I figure out what is the leap that the life would have to undergo here to make it to there in order to understand what challenges that environment presents. So we play this comparison game. We'll take an environment on Earth and an environment on Mars, and then we start parsing out the distinctions. What are the measurable differences between them? The one on the top is a place called Palander. It's on part of the archipelago Svalbard, the northernmost island called Nordaustlandet. And it looks pretty barren, right? And having been there, I can tell you there's a lot of life there. It lives in the rock. We're going to talk about life that lives in rock in just a moment. The one on the bottom is not Earth. That's Mars. John, is that Victoria? Okay, I think it was Victoria, right. So that's a crater on Mars, or not a crater so much as a canyon there. It is a crater, but what I'm showing you there is the steep wall and the drop-off, just like I'm showing you the steep wall and the drop-off on the top picture. And the reason why I'm showing you this is there are a lot of similarities between these two things. Sure, you have this very thin sheet of ice on the top image. But what is interesting is that all the life is not in that ice down there. All the life is in the rock, in the layers of the rock. Little organisms are living in the pore spaces of that rock. So you can't help but look at a picture like the one on the bottom and say, okay, there's layers in that rock too. What's going on in those pore spaces? How big are those pore spaces? Can they hold water? What happens when winds blow and you weather the top of that rock? Does anything happen to exchange the chemical elements on the top surface of the rock with the inside of the rock? So these are questions that we ask because we want to know. On Mars, can something live in the rock? It certainly does on Earth. We have organisms on Earth that, as their metabolism, they breathe metal. So why can't we have that on Mars? We could have it on Mars. We go to extreme environments on Earth. We try to get as close as we can to the other planets. We can't get very close because there's nowhere we can go on Earth where there's nothing. And we've tried really hard. The picture on your left, that is a volcano that's highly weathered. It's a subglacial volcano, also in Svalbard. The upward protrusions are old weathered volcanic pipes. And the reason we go there is because as that rock weathers, it makes minerals that look a lot like minerals that have been found in meteorite that is known to come from Mars. It's a very famous meteorite about which we argued a long time ago whether or not it had evidence of life. And so we go there to study that rock and see, do organisms live in that rock? The image on the top, sort of to the right a little bit, that's Badwater Basin in Death Valley, another extreme environment. It's extreme in a number of regards. First, it's very, very dry most of the time. There is a rainy season where it becomes periodically inundated. And during that time, like that, life comes flowering into the evaporite minerals as the water retreats. And that white stuff that you're seeing on the surface there, those are evaporite minerals. The top layer there, in this particular case, was the mineral, the sulfate mineral gypsum. And I'll show you a picture of the life that's living in that soon. It's also extreme because it gets so hot. And then, as you know, Death Valley National Monument, this is the lowest level of land in the continental US, I think in the world actually. And then the one beneath that image is from one of my favorite extreme environments, which is the McMurdo Dry Valleys in Antarctica. That particular one is called Battleship Promontory. And I took a few people there with me on an expedition in 2005, and we spent a month there trying to understand the organisms that live in the rock there. There's nothing else that lives in that particular area of Antarctica. So, when we say extreme life, what are we talking about? And the answer is, it depends. Some of the specifics about extremophile conditions that we might try to understand are how hot can life tolerate? How cold? How much pressure? Can it live in a vacuum? What about extremes of pH? Some environments are extremely acidic. I'm going to show you a picture of another place I've explored that has a pH of 10.5. It's basically soap. How much radiation can life tolerate? What about sun? If you go to an area with no sunlight, what do you get? Desiccation. How dried out can you be? Now, when we talk about extreme organisms, we're not just talking about can you pitch a bunch of bacteria up into the stratosphere and have it survive until it settles back down to Earth. We're talking about life that actually sets up shop and thrives in the environment. Somebody mentioned before the hydrothermal vents in the deep sea. I did get to go to the hydrothermal vents in the deep sea also in 2004. Filmmaker James Cameron was making a movie to prototype the techniques that he used for the movie Avatar. And this is when I was at JPL, and he invited us to come along, and that if we could come up with a scientific instrument to do some good experimenting at the seafloor by the hydrothermal vents, we could go. And my bosses at JPL said, okay, and we designed and we built this instrument, and we took it to the field, and we deployed it on a deep sea submersible. The deepest dive I went was 3 miles down in the Sea of Cortez in the Guaymas Basin, but we also went to some other locations in the Pacific. The image on the far left, these are the famous tube worms that live at hydrothermal vents. This is an example of an organism that thrives in this really peculiar environment. It is dark. It is hot. It is very high pressure. In fact, one of the games that people play when you explore deep sea is to take styrofoam coffee cups with you in a net bag all the way down, and when you pull them up, they're as big as a shot glass. And that's how much the pressure affects whatever is there. So the tube worms are able to withstand this high pressure. The image at the top, those are little shrimp that live in pretty high temperature environment right at the smokers. This one is a jellyfish that's right underneath it. The one to the right is a little bitty octopus, not squid. This one's an octopus. The image above it, that is the only one that isn't from Wikimedia. The one on the top is from that exploration down at the hydrothermal vent that I told you about. And those are little very high pressure, very deep sea crabs. Interesting thing is when you look at the organisms that live there, the shrimp, the octopus, there's fish down there. These things have eyes. What are they looking at? There's no light. One scientist, Cindy Van Dover, came up with a hypothesis that these eyes are actually optimized for different wavelength, infrared, that might be able to help them seek the heat to stay close to that source. So I don't know where the state of that research is presently. I haven't been doing hydrothermal vent research in a number of years now. But the take-home story here is there's no light there. It's very high pressure there. The thermal gradient is very extreme. So it's boiling water coming out of the black smoker. It's not water coming out. It's smoke, it's minerals, it's dust that's crystallizing as it comes out. The water becomes heated right there. But as you move more distal from the smoker, it becomes colder. And by the time you're a few feet away, it's back to its nominal temperature, which is just a couple of degrees above freezing. So if you live in that environment and you see these little organisms moving from the vent to several feet away, you got to ask yourselves, guys, it's 100 degrees here and it's 2 degrees there. How are you doing it? This is really important because this is not just a temporary thing. These organisms are adapted as communities living in this very extreme and changeable environment. If we go to the next slide here, this orange stuff that you see, that's a type of bacteria. And what is happening at the hydrothermal vent is it can be very, very acidic right there by the vent. And you change the supply of chemistry as you move further and further away. So you see organisms of microbes, some of them reduce oxidized materials. These are further away from the vent. And some of them oxidize the reduced materials that are coming out of the vent. So what this means is there's an organism for all seasons in terms of acid and base. So in terms of chemistry, life is always all about trying to buy or sell an electron. That's how we do metabolism. And so when you see organisms that take advantage of extreme acid or extreme base, and then you see communities of organisms working together, basically working that chemistry so that one man's energy and food and nutrients is another one's poop and so forth, and then they keep cycling. That's how you establish community. So that's an important lesson for looking in extreme environments. You can't just find an organism that seems to do okay. You have to find a community. In ecology, in extremophile biology, in space exploration for astrobiology, you can't just do one thing. You have to do a bunch of things. So an organism by itself is not as important as finding a community, because you could find a stray organism that has somehow been seeded or is contamination that doesn't belong in that environment. But when you find the community, you know that you can take up residence in that extreme location. So this brings me to an important point, and that is that there are some organisms that are considered very extreme because they can withstand huge plunges in temperature and pressure, all kinds of different environmental stressors. But they don't prefer that. They can last a long time under those environmental stressors. And the tardigrade is one of those. So it's not an extremophile in the strictest sense, even though it can withstand a lot of stuff. And so I like to draw the line when I'm studying extreme environments and extremophile organisms at, can you establish a community and really thrive there? So let me take you on a tour of some of my favorite extreme environments and talk about who's living there. I told you a little bit about Battleship Promontory already. It's a protected environment in Antarctica, and it's famous because it has this sandstone, which is really interesting. It's such a white, pure quartz sandstone. It looks like Wonder Bread in the clean part of it. But there are these rocks nearby. They're called dolerites. They're a type of basalt. They have a bunch of iron. And you get these winds howling in the dry valleys. And the winds pound the rock, and they blow debris at the rock. And then some of that debris lands on this sandstone. And it just so happens that organisms live in the pore spaces of that sandstone, and they use that metal for their metabolism. So I'm going to show you a little bit about that. So when we were there, we camped there and we studied the range of temperature change just over a very short time. It's only a month, and it's in the the Antarctic summer, really. So this doesn't give us a glimpse over the whole year. And there are sensors that have been stored there. But what we wanted to see is what we could measure about these organisms and see how it affected our sampling rate. So how often do we need to sample? Is it daily? Is it a few times a day? Is it once a week? In order to see any kind of change in the chemistry. Why do we do this? Because if you were to just approach a rock and you were on another planet and you had limited resources, you would want to know how much stuff do you have to measure before you expend the resources to drill into that rock. Now, John and I, on a daily basis, are asking ourselves this question with Curiosity Rover in Gale Crater. Is this rock worthy? Is this a meritorious location? Because it takes a lot of time and energy and resources to drill a hole in a rock and take the powdered material and analyze it. So we want to make ourselves the best possible opportunity to get good science by picking the right rock. So when we went to Antarctica, what we were trying to understand is how to pick the right rock that has living things inside of it. This picture on the right, you see that little scale bar, the black and white thing? Those are centimeters. Each little strip there is a centimeter to give you a sense of scale. Now that reddish, orangish stuff on the surface is oxidized iron. And what happens is organisms can use reduced iron, they oxidize the iron, and what you end up with is a relationship with other organisms that can do the opposite. Take the reduced iron and oxidize it, take the oxidized iron and reduce it, mix in a few cannibals, that is, heterotrophic microbes, and they eat the guys that are making their living through what they call chemolithoautotrophy, which is a fancy word for a type of synthesis that uses rock instead of sunlight. And then you get this whole community thriving in the rock. So one of the consequences of communities thriving in the rock is as they emit gases, the skin on the rock peels off. So, thing one, when you're looking at these rocks, find the rock with the skin that's peeling off, because it might have something that's making the skin peel off. If you look more closely, you begin to see some features of the rock that are important for organisms if they're going to take up residence. One of them is the amount of space in between the mineral grains. So it's a pretty coarse sandstone, this sandstone. In the image on the top left, you'll see the lens cap from my camera there on the left to give you a size of the scale of that rock. The image on the bottom of the screen is a photograph taken with a scanning electron microscope. And the size of the scale bar on the bottom, I don't know if you can see it in this light, is 200 microns, or micrometers. And so those look like big gaping caves between the grains, right? And so in those big gaping caves, you can retain water and nutrients and your waste products. And this is important because you need to be able to retain the stuff you need, but you have to have enough porosity to diffuse away the bad stuff, or you will drown in your own poo. And that's how these communities are able to establish residence, because it's the right porosity, the right extra nutrients from the dolerites being weathered, blowing there. There's a little bit of snow and rime ice to provide some water. So it's an ideal environment if you are a cryptoendolithic microbe that is living in the pore spaces of rock. Cryptoendolith means not, I thought originally it meant cryptic, hard to find, but I was wrong. It actually means crypt, meaning the space in between the grains. You see in that image on the upper right, the green stuff? That is cyanobacterial members of that community. Isn't that cool? By the way, there are also green sulfur bacteria in this rock. So let's switch gears for a second and talk about other types of extremophile organisms. Now, this is a really interesting microbe. It takes what is a toxin on Earth, perchlorate, and reduces it, and that's how it breathes. That's its metabolism. An unusual thing about this, well, there are a couple of unusual things. Not only does it reduce this poison, perchlorate, but this thing is magnetic, this bacterium, meaning it responds to a magnetic field by alignment. Another thing is it is extremely radiation resistant, and it is extremely desiccation resistant. Now, I can think of a place that has a lot of perchlorate, is really dry, and has a lot of radiation. And it's not on Earth. It's Gale Crater. Now, does that mean that we should be looking around for this type of organism? I don't think we can go prospecting for specific organisms, but this is how your mind is supposed to work. You think about what the environment presents. You find the most extreme organisms on Earth that might be able to be survivable in that environment if they kicked it up a notch. And it gives you a model you can pursue for trying to discover whether or not there's life there. So here's a close-up of this organism. It's called Deinococcus Radiodurans. And this is an environmental microbe on Earth, and we even find it in areas near nuclear waste and so forth. It's a very hardy organism. And the researchers that identified this organism, I've shown their images here. They are John Coates and Lori Achenbach. And this is from a paper in 2004. Now, let's go to this discussion again about pH. So how much acid, how much base. And this is really important because you have to employ a different strategy depending upon the chemistry of the environment. So the one on the left is called Rio Tinto. It's in Spain. And this is an environment where you have a lot of iron. And you have reduction of iron by some bacteria that are reducing oxidized species. And you have oxidation of the reduced species of iron by the companion species. And you make this community. In the image in the middle, that is Mammoth Hot Springs in Yellowstone National Park. And so it's a very acidic, sulfur-rich environment where you have to be able to withstand very high temperatures. Those are some pictures of what we call hypothermophile bacteria up in the upper right hand, meaning they like it hot. And then the one in the just beneath that, it's a 7 o'clock. That is from Missouri. That's acid mine drainage. So in the case of acid mine drainage, it doesn't make a river devoid of life. It makes it devoid of the life that we know and love and can use. There are plenty of microbes that would be happy to take up residence amongst that heavy metal environment. So once again, the choices that we make do affect the environment and provide opportunity for extreme life. If that's what we want to do, that's fine. If that's not what we want to do, we have to think about how we handle that consortium of life. So let's go to high pH environments. This is the environment I told you about where it was 10.5. This is Mono Lake in Mono County, California. And it is a very unusual environment. There are young volcanoes there. It's really cool, lots of obsidian lying around. And what is so interesting is there are these jets that come up from beneath the lake that have carbon dioxide. And the carbon dioxide jets hit the cold water and they precipitate out carbonate. And they make these towers of carbonate, and they're called tufa towers. And they're very interesting, and they're organisms that live in the tufa towers, more of these cryptoendoliths. But the major, how shall we say, consortium, food system, ecosystem of Mono Lake is based upon these shrimp. There's a close-up of that shrimp on the right side. They're a brine shrimp that lives in this very alkaline environment. And the brine shrimp are in turn eaten by flies that are attracted to the brine shrimp. And those are in turn eaten by the California gull, which is the bird you see. It used to be during times early in the continental U.S. when we were inhabited by indigenous peoples. They would eat some of the brine flies because they were a very protein-rich environment, especially nomadic indigenous Americans. So that's Mono Lake with the very high pH environment. I'm taking you back to Badwater Basin again because I want to show you this. See the rich green stripe going through the hand sample? That's just the light-using, photosynthesizing microbes. Beneath that, there are other microbes that can use the minerals and also some heterotrophs that can eat those other guys. So once again, you establish a community, and they exist just fine until the water runs out, and then they go dormant in a spore form, and then they are revived again the next time it rains. In cold, it's not always cold and dry. Sometimes it's cold and pretty wet. And we have lots of snow algae. I've seen it in a lot of places in the Arctic, both in Svalbard and also in Canada. This is the Llewellyn Glacier in British Columbia, very, very close to the Yukon Territory. And it's kind of reddish, but there are a number of colors of snow bacteria depending upon what types of pigments they have. And so this image on the left, it looks like a painting. Doesn't it look unreal? And I stood there in front of it and took this image, and even I thought it looked unreal. And all that stuff, the grayish, reddish cast is snow algae, just thriving there in that environment. So if you want to look at an environment that is as seemingly barren as this one is, and this is back to Gale Crater on Mars, you really have to consider what you would have to do in order to be able to withstand that environment. And all the places we explore on Earth inform us about how to look and where to look and try to imagine what the life would be like in such a seemingly hostile environment. I always go back to this planet because this is the test bed I can get to, and it's a really long commute to Mars, and I just don't want to do that. So the extremophile life on Earth is not that extreme if you're adapted to those specific environments. Extreme is in the eye and concept of the beholder. Adaptability may be the most extreme state of life. Life that can be very adaptable until its evolutionary path catches up with its new environment is the life that's going to survive. So it's a giant universe out there. There's lots of stuff to do, lots of questions to ask, and lots of places to explore. I'm not going to touch hardly any of it in the remainder of my lifetime, but I hope some of you will. And I'm going to stop here because I want to leave time for all the questions that you couldn't ask before we started talking. And one last thing, and that is I did not put my email address on this slide as I typically do at the end of slides. So if you have questions, I'm really easy to find because I'm at Goddard and all of my information, if not made publicly available, has already been hacked. So write me and I will answer you.
See if I can figure out how to turn it on.
It's probably the button that says on.
Don't see a button. Mike? Look at that. Questions for Pam? Please state the question, then I'll repeat it, and then Pam will answer, I hope. Yeah, go ahead.
Last couple of days, I saw a note that said that the Rosetta craft has found glycine and phosphorus on Churyumov-Gerasimenko, and which means that these comets not only could have hit Earth, but it probably hit Mars. So any comments on that?
The question is glycine and phosphorus found by Rosetta on a comet. What does this mean in terms of comets hitting Mars and the Earth and the implications for life? I think I got the gist.
Yes, isn't that cool? So the implications are, of course, that the more you exchange materials, the more possibilities you have for essentially seeding the stuff that you need in a lot of environments. Whether it means that the glycine inventory that we have was seeded from a comet, as some people have proposed, not only just things like amino acids, but also water, this obviously lends credibility to that story. The thing about whether or not the sequence of events was take these amino acids and phosphorus, send them to Mars and send them to Earth simultaneously, or send them to one and then one feeds the other. You could have any number of permutations about those relationships. So the more places and the greater diversity we find, the more probable it is that materials have exchanged.
And back, yes, sir.
So you go to these deep, dark vents, and where everything is the whole lot's in the dark, and then you hit them with really bright lights to get the video and photography. Is there any concern that those lights could actually hurt or kill the organisms?
So when you go to places that are really dark and deep in the ocean and you hit them with bright lights, is there any concern that that's damaging the organisms?
I was worried about that. I couldn't find enough literature to know whether the brief transient effects of that would create a long-term harm. I just don't know the answer to that. But I have to imagine that it was at least disturbing. One experiment we did was to turn off all the lights on the submarine, settle on the floor, which is actually kind of scary, and take our spectrometer and try to observe whether or not we could detect any native light, because we had very sensitive photon counters. And we did see a blue wavelength issuing from the vents, which is possibly proof of the theory that Cherenkov radiation comes from the vents. But yeah, maybe we damaged some life. That's a possibility, and that's something that you always have to worry about.
I'm going to work my way around this way, so don't worry, I'm coming over here. Way in the back there, and then I'll come to you, ma'am. No, you're, yep.
Okay, I have two questions. With the Curiosity rover, what are you hoping to find in the rocks that would indicate an environment or ancient or existing life? And also, what about like methane-based life on Titan in terms of?
I'm sorry, I don't hear the second one.
Okay, I'm sorry.
Well, I didn't hear your second question.
In terms of extreme environments, do you think there could be methane-based life on Titan?
So with Curiosity, what are you hoping to find that is going to lead you down the road to understanding whether or not there was life, habitability, and do you think there's methane-based life?
On Titan.
On Titan.
Yeah. Okay, so question one, we hope to find the same things that we look for on Earth when we're trying to understand the past, and that is to understand the sequences of environmental change that are locked up in the stratigraphic record. So what we're looking for is to try to understand the pace of change of the surface of Mars and whether there's chemical evidence that shows us that, oh, there was a whole bunch of organic chemistry here and then it stopped, or we had none and then we got some. And so it's the same kind of prospecting we do on Earth. Now, the second question, could you have methane-based life? I'm guessing you don't mean constructive methane, but you mean life that has a methane metabolism. And so I don't know very much about Titan, except that I do know it's rich in hydrocarbon. And whether or not it possesses other physics requirements that would enable methanotrophy to happen, I don't know, because things like the pressure requirements and other types of thermal requirements for methanotrophs on Earth, I don't know whether they pertain to Titan or not.
Here, ma'am, and then behind.
Can we take organisms that live in extreme environments here, to us as being extreme environments here on Earth, and take them someplace like maybe Mars or Europa and like analyze to see how the lifespan works there, and take that information to see how we can support how we're going to have life, or to even have humans to travel to those kind of environments?
A planetary protection question. Can we take life from extreme environments on the Earth and take them to places like Mars or Europa, see how they behave and or adapt and how they might affect and respond to human life there as well?
A lot of people ask that question and have suggested that there's this international committee called COSPAR that has conventions about how we will treat other planets. And one of the most important considerations is that we do not contaminate another planet that could have a potential ecosystem with our own stuff, and also that we would not bring potential contaminants from another place to here without understanding what level of harm could happen. So in that regard, by convention and by agreement, we can't really just bring stuff to other planets, although I know people have suggested that we do so. So a way around that is to bring organisms to the International Space Station, which responds to the question earlier about how useful that is. So that is something that can happen in terms of trying to understand whether those organisms can adapt over time. And if they don't adapt, why not? And what can we do to provide protections so that those organisms can have a combination of adaptation and protection in order to be able to thrive in an extreme environment. With regard to whether or not that helps us understand our adaptability, microbes are much more robust and cosmopolitan than animal life, particularly humans. And so the level of adaptability from a microbe is going to be much greater than the adaptability of a human. So we would still need to understand the humans by sending them to the International Space Station.
Yes, sir.
Have you any insights into the role of tholians in any of your or your community's work in the recent past?
Do you have any insight into the use of, I think he said, tholians in your research into communities? Am I repeating that correctly?
Well, have you found in your research or in the community you're in research the role of tholians in any of this?
What if any, role do tholians have in your research?
So when I first started working at JPL, I had a colleague named Gene McDonald who had recently come from being a postdoc with Carl Sagan, and he had worked on tholins on Titan. And so I don't, and I haven't explored that, but I do know that there is a community of chemists who have.
Okay, working this way? Yes, sir. I'm coming down here. Yep.
We're all a product of our experience, and no matter how many brilliant people we have like yourself, you think outside of the box. You can only go so far in our imagination and in our science. So what's the chance that no matter how brilliant and creative we are, we march ourselves down a path that has no relationship to what's out there, and then we'll never find it because we live in a narrow sphere of the potential of the whole universe.
So let's see if I can paraphrase that. What if we have too narrow an outlook to be able to appreciate the perhaps range at which life may or may not occur in the universe, such that we would miss it because we're not looking at that breadth of possibilities?
Well, that's a really important and a really good question. It's very hard to, first of all, remove our Earth-centrism because we're from Earth. And also, yes, it's possible we'll basically screw up. So I don't feel deterred by the possibility that I'll get it wrong, because humans get a lot of things wrong before they get it right. And that's how we learn. And I think that we learn something from the trying, and it may be an important part of our development. Certainly, tech development happens that way. We do the best we can, and we try to get the broadest possible model. We try to not be too model dependent so that we can be responsive to discovery that might lead us down a different path. But sure, it's possible we'll do the wrong thing. The only thing that we can do, we have one choice: to do nothing or to do something, and try to constrain the probability that the something will bear fruit. But you're right, there's a possibility that we'll get it wrong. So we'll just do it again until we get it right.
Down here first and then there. And that, I think that should probably be two more. Yeah, so here and then here. Yep.
So,
Yeah.
Doctor, you told us a lot about that Mars is an incredibly extreme environment today, more extreme than anything on Earth. But you also said Mars had some really bad things happen in the past. Lost its dynamo, lost its magnetism, lost its atmosphere. I realize our data is very finite, but is there some speculation that maybe a billion years ago, life was very abundant on Mars and literally the whole planet went extinct?
So the question is, we know that Mars has had things happen to it, lost its dynamo, et cetera, et cetera. And so it's a very different place now than it was billions of years ago. Has there been much thought about the possibility that life thrived there in the past and it's not there now?
We do ask ourselves that question. And so what we do is two things. One, we try to find the right window in history, and we try to find the right conditions spatially on the planet. The problem with Mars is not that we don't know when in history to look. It's where to find that moment in history. The late heavy bombardment took place 4.1 to 3.9 billion years ago. So if Mars was formed 4.6 billion years ago, there's like this 500 million year window when stuff could have been happening. That is not inconceivable. But there are lots of factors that would govern where that would be on the planet and how and where we would look for the evidence now. We've been staring at image after image, John for 2 missions, me for just 1, trying to understand what is the best rock to look at, the most promising rock to look at, and what we get is that it was definitely better in the past. We definitely know there was water on the surface of Mars. We see the evidence that there are hydrous minerals. So if it were me, I would be looking down deeper. But our technology is not there yet. We just can't go 15 meters beneath the Martian surface. It was really hard to get to the place where we could drill down 5 centimeters. So if we look for the right window in time and we look for the right place spatially, I think that we can find some evidence of a very much better environment. Whether or not life was thriving and all over the surface of Mars is a different question. If it was, the evidence of it is not abundant where we are looking now. It's not abundant where we have been looking with Opportunity or where we were looking with Spirit or any of the other previous missions. So we'll keep looking. It may have been very abundant at one time, but it would have to have been a time before all the resurfacing of Mars.
Okay, last question here, sir.
What is your basic definition? What is your criterion for declaring that you found it on a planet?
What is your definition of a living thing, and what is your criterion for declaring you found it on another planet?
Fabulous question. I'm not even going to try to define a living thing. So I do this a different way. I say, I know what a mineral looks like. And I know they are all through the observable universe. So if we can pick out the chemistry that's indicative of a mineral, and the chemistry that's indicative of an atmosphere, and then we find some chemistry that I don't know what the heck this is, we've narrowed the search space, and that's possibly something that could be associated with life. Does that prove it? No. Now, when you're looking at the criteria for establishing proof of life, we don't have consensus on that. So that is a really tough problem. The reason is because we only know what we might look for to prove that we have found life on Earth. We don't know what life might even look like somewhere else. So that part we can't do yet. But what we can do is say whether or not Mars is habitable or uninhabitable. And we can say whether Mars looked like it was getting better or getting worse as time went on. And that's why we ask those questions.
Okay, help me thank Pam once again for a amazing lecture. I'd also like to thank once again our sponsors, Aerojet, Rocketdyne, and United Launch Alliance. Thank you very much for your support. couple of announcements. First, the public observatory is open this evening and will be open until 10 p.m., so you've got about an hour to get out there and have a look at something cool. Many things cool.
At Mars.
And then, in fact, Mars. And be sure to join us again for the last lecture in this series this year on June 23rd, when Dave Charbonneau from the Harvard-Smithsonian Center for Astrophysics will talk to us about how to find an inhabited exoplanet. Thank you all very much for coming. Enjoy your evening.